Have you ever wondered why two oceans meet but do not mix? This curious spectacle of nature has captivated the minds of many, and it's not without its fair share of myths and misconceptions. Imagine this: two bodies of water, side by side, refusing to blend into a unified whole. It's almost like they have their own unique identities, steadfastly refusing to relinquish their individuality. Many attribute this to a divine intervention or mystical forces. But is there a more rational explanation? Could it be due to differences in their salinity, temperature, or density? Or perhaps an invisible boundary shrouded in the complexities of oceanic currents and tides? As we journey through this fascinating topic, we will unravel the common misconceptions surrounding this phenomenon and shed light on the science that governs the unique behaviors of our planet's oceans. Today, we will dive into the science behind this fascinating occurrence. To understand this phenomenon, we first need to explore the basics of oceanography. Oceanography is the scientific study of the ocean, and it encompasses a wide range of topics. But for our purpose, we'll focus mainly on three key factors: water density, salinity, and temperature. Let's dive right in with water density. It's essentially a measure of how much stuff is packed into a certain volume of water. This stuff can include anything from tiny particles of sand to microscopic organisms. Water density is crucial in the ocean because it influences how water moves. Denser water tends to sink, while less dense water rises. Next up is salinity, or the saltiness of the water. The ocean isn't just pure water, it's a soup of different minerals. And salt is one of the main ingredients. Salinity can change based on factors like evaporation, ice formation, or the input of fresh water from rivers. And just like density, salinity plays a big role in the ocean's movement. Higher salinity means denser water, which tends to sink. And finally, we have temperature. It may seem straightforward, but temperature in the ocean is a complex affair. The sun heats the surface water, making it warmer than the deep water. This creates a temperature gradient with warm water on top and cold water below. Again, this affects density, with colder water being denser than warmer water. So how do these factors tie together? Well, they all contribute to something called ocean stratification. This is the layering of water in the ocean based on differences in temperature, salinity, and density. It's why you might feel a sudden temperature drop when you swim a little deeper. It's also why certain parts of the ocean can have different colors or appear not to mix. Now, equipped with these basics, we can understand why oceans meet but do not mix. Now let's unravel the mystery behind the meeting of oceans. This phenomenon, where two bodies of water visibly meet but don't mix, is a fascinating spectacle that has puzzled observers for centuries. But what's the science behind it? Well, it's not as mystical as it may seem. It all comes down to three key factors: density, temperature, and salinity. Let's start with density. Density is the mass of a substance per unit volume. It's why a rock sinks in water, but a cork floats. In the context of our oceans, water from different sources can have different densities. This difference is primarily due to variations in temperature and salinity. So let's talk about temperature. Water's density is affected by its temperature. Cold water is denser than warm water. This is because when water is heated, the molecules move faster and spread apart, making it less dense. In contrast, when water is cooled, the molecules slow down and come closer together, making it denser. This is why we often see a layer of warmer water, known as a thermocline, floating above the colder, denser water. Now, onto salinity. Salinity refers to the concentration of salts in water. The more salts a body of water has, the denser it is. This is why the Dead Sea, with its high salt concentration, is famous for allowing people to float effortlessly. In the oceans, variations in salinity can occur due to factors like evaporation, precipitation, and the melting or freezing of sea ice. To see these principles in action, let's take a trip to the Gulf of Alaska. Here you can see a stark line where the dark, cold, and saline waters of the Pacific Ocean meet the lighter, fresher waters from nearby rivers. These two bodies of water have different densities due to their variations in temperature and salinity, and so they don't readily mix. Instead, they form a boundary, a line of demarcation that's visible from above. However, this doesn't mean they never mix. Over time, through a process called diffusion, molecules from each body of water will gradually intermingle. This is a slow process and can take a long time to noticeably change the composition of the two bodies of water. Furthermore, external factors like tides, currents, and wind can also cause mixing. For example, when strong winds blow, they can create waves and turbulence, which can stir the waters and promote mixing. So it's not a mysterious force, but rather the laws of physics at play that prevent the oceans from mixing. These laws govern everything in our universe, from the smallest atom to the vast oceans. And by understanding these laws, we can better appreciate the wonder and beauty of our natural world. With the science explained, it's time to debunk some myths. You see, the natural world is a complex tapestry woven with intricate details and fascinating phenomena. However, when these phenomena are misunderstood, myths and misconceptions tend to take root. One such myth is the belief that the oceans that meet do not mix. Let's clarify this. Firstly, the idea that these bodies of water are like stubborn enemies refusing to mingle is quite far from the truth. While it's true that these bodies of water exhibit different colors, densities, and temperatures, they are not permanently segregated. What we witness is not a permanent boundary, but a gradual mixing zone. Here's an analogy for you. Imagine pouring a cup of hot coffee into a mug of cold milk. Initially, you'll see a clear distinction between the two. The coffee floats atop the milk, forming a distinct layer, but give it some time. Gradually, the coffee and milk begin to blend, creating a delicious concoction. The meeting of oceans works in a similar manner. The stark contrast you see is temporary, the result of immediate differences in temperature, salinity, and density. Another misconception is the belief that these waters remain distinct due to religious or supernatural reasons. While it's understandable that such awe-inspiring natural phenomena can evoke a sense of wonder and mystery, the explanation is firmly rooted in the realm of science. The differences in physical properties and the forces of nature, such as wind, waves, and currents, contribute to the mixing of these waters over time. Lastly, some folks believe that these waters are harmful or dangerous to cross. Again, this is not the case. While navigating such areas might present challenges due to differing currents and temperatures, they are not inherently perilous or harmful. Understanding the truth behind this phenomenon allows us to appreciate the intricacies of our natural world even more. Remember, knowledge is power. The more we understand about our world and its fascinating workings, the more we can appreciate and protect it. To sum up, the phenomenon of oceans meeting but not mixing is not as mysterious as it seems. When we first encounter such a sight, our minds may be filled with wonder and intrigue. But as we've delved deeper, we've seen that science holds the keys to understanding this captivating spectacle. At the heart of this phenomenon lies the concept of density. When two bodies of water meet, their densities play a pivotal role in determining whether they'll mix or remain separate. The heavier water sinks beneath the lighter one, leading to that distinct boundary we often see in photos. Temperature plays a significant role as well. Cold water is denser than warm water, so when a cold current meets a warm one, the colder water will dive beneath its warmer counterpart, creating another layer of separation. Next is salinity. The saltier the water, the denser it is. When a salt-laden current comes into contact with a less salty one, the denser water slides underneath, refusing to mix. These three factors, density, temperature, and salinity, are the pillars of this phenomenon. They work together in a complex dance beneath the surface of our oceans, crafting the captivating illusion of two bodies of water refusing to blend. But it's not just about the spectacle, the curiosity, or the intrigue. Understanding this phenomenon is a testament to the power of scientific knowledge. It's a reminder of how science can transform something seemingly mystical into a comprehensible, explainable event. It's about debunking myths, replacing them with knowledge, and fostering a deeper understanding of our world. So the next time you stumble upon an image of the Atlantic meeting the Pacific, or any two bodies of water coming together, remember the intriguing interplay of density, temperature, and salinity. Remember that beneath the surface, there's a world of science at work, weaving a tale of natural wonder. So next time you see a picture of two oceans meeting, you'll know exactly what's happening beneath the surface.